Okay, so the proof of the theorem is shorter than the comments concerning it. Okay, we have to use our basic Fourier theory. So consider these coefficients an, which are integral between minus a over 2 and a over 2 of f hat omega times e to the 2 by I n omega over a d omega. Well, by Fourier inversion, because the integrating between minus a over 2 and a over 2 is like integrating over r, because f hat is supported in here. So this is Fourier inversion says that this is f of n over a. N over a. On the other hand, and it's not fn over a in some very vague L2 sense, because the function f is continuous, so it's f computed at the point n over a, but the real. Okay, so okay, since an, so these are the Fourier coefficients of this function, then f hat omega in the L2 sense can be written as 1 over a times sum over n between minus infinity and plus infinity over a n of f times e to the minus 2 by I omega n over a. That's a Fourier theory version, which says that I can reconstruct a function in L2 of the interval minus a over 2 by its Fourier series. But that's 1 over a and sum over n over, and this we said it was f of n over a times e to the minus by I omega n over a. Well, now I reconstruct f. So f of x, which is equal to the integral minus infinity plus infinity over f hat omega times e to the 2 by I omega. So we remember with signs d, and that's still for the inversion. But then we have the f hat was supported in minus a over 2, so I can replace this by minus a over 2, I can replace this by a over 2, which is exactly the same, and then I replace this expression here, so that's the integral. Well, I exchange sum and integral, sum over n, f hat n over a, then the integral minus a over 2, a over 2, of what do I have? I have e to the 2 by I omega e, but also minus n over a d omega. And this is a I can compute this integral, right? That's like sum over n of f. This was f, no, f. Was this one, f of n over a times and then we get e to the 2 by I omega t minus n over a over 2 by I t minus n over a between minus a over 2 and a over 2. And when you do the calculation, that's like n over a. And this is a sign, right? 2I, and that is a sign over something, translation, and you get I give you this. Right, because we get the sign of 2 pi times t minus n over a times a over 2. Times a over 2, it means that 2 and 2 go away, so I have pi a times t minus n over a. By a times t minus n over a. Over, oh, I forgot. I forgot something. Because I didn't get the right one. I forgot the 1 over a, which is y. Okay. The denominator I get pi times a times t minus n over a. Okay. Now, actually, okay. And this is a so the proof from the proof we get some more information. For instance, I read because there are always these constants. So the integral, so we get some isometry relation, which is that if I consider the integral, the L2 norm of f, if, which is the same as the integral that we know, but this one is sum of the Fourier coefficients square, because that's this is the isometry for Fourier transforms, and this is the isometry for Fourier coefficients, and this is 1 over a and n over a not square. And if you read the beginning and the end, it looks like a miracle that not only can reconstruct f from its samples, but the L2 norm of f is exactly like the little L2 norm of the samples. And then something we get. So that's we get the isometry relation. And then we also get reproducing formula. So the reproducing formula, it is like this. So for Z and W, I guess I can identify that to be complex number. Set K Z X. I'm sorry, for Z, a complex number. Consider the function having Fourier transform e to the minus 2 pi I omega Z over A times the characteristic function of the interval A over 2, because this is something we integrated, in the course of our proof, which means, okay, that K delta T is equal by Fourier inversion of the integral of K Z omega e to the 2 pi I omega T omega, and this means that we are integrating between minus A over 2 and A over 2 an imaginary exponential, which is the calculation we did before, and we got a sink. And so what we get, in fact, it is, if you do the calculation, what you get is almost the sink. It is A times the sink of whatever it is. Pi A so consider this function here. So it's the sink function. It is the sink function having kind of center at Z. It means that when t is equal to Z, it is 1. That's all the function A. And it is a 0 when t minus Z is a multiple of 1 over A. Okay. Now, Shannon's, this is a formula here. So Shannon formula becomes f of t is equal to 1 over A times sum for n minus infinity plus infinity of f n over A times this is same function here, A times the same function, which means that this is K, the point where we want to put that. Okay, n over A at t. So I can write, this is just another way of writing the formula. So the fact so what is the, okay, this is Shannon's formula. What is the reproducing formula? The reproducing formula is that f of x, f of t, which is like the integral between minus a over 2, a over 2, and omega, that's e2 by I omega t. Okay, this is the inner product. So let me write this. Let me minus this is a bar. This is the inner product between f x and the function by I. It's the integral of this times that conjugate, and this conjugate is like this times the characteristic function of this conjugate, like that. And by the two isometries, it is the same as f times the Fourier anti-transform of this, which is for kt of R, which means that we have okay, so what is the, if you look at the beginning and the end of this calculation, you get that f of t is the inner product between f and kt in 2 of R. But both functions are in the inner space. So it's the same as we know over that. And kt clearly belongs to the very inner space. Because kt is a function whose Fourier transform is supported between minus a over 2 and a over 2, yes, and it is in a 2, it's even bounded, so yes. Okay, this will become starting tomorrow, I guess. No, maybe. Are you going to talk tomorrow about? No. Okay, this will become not tomorrow, next week, a kind of refrain, discourse that we had a Hilbert space of functions, this one, in which the values of elements at points can be written as the inner product of my element with what is called the kernel function. But then we will develop here. So let me just mention that. Ronstein in 1945, which is 1 year after, 1 year before, together with Chang. Although maybe it was started before by Bergman. The axiomatics were laid down by this guy. Over there. Okay. By the way, okay. as an easy exercise. You can show that if I consider the inner product, remember this is L2 functions which support minus a over 2, a over 2. This is a times n, which is a times 0 or 1 and which means that these reproducing functions that appear in this reproducing formula. Okay, if I take the parameter of the function equally spaced, they form a orthonormal system. This is a Holy Grail. Okay, this is so you have ortho normal ortho. Well, back to the a vector, you kind of a Holy Grail. Which means do not count on it in any very rare. There is a Russian school that studying for which Hilbert spaces are functions. You have a almost orthonormal system, which you get an almost Kronecker symbol for using reduced functions. Okay. I don't know if I have something. Okay. So let's write this. Okay, so this easy exercise says, but you can put it also using this here, because I guess no, using the isometry. I don't know. It's an exercise. You can use it using it.
Sorry, Nicola, what have you written in the last line? Only I don't read.
Holy Grail. Holy Grail.
Okay, is a person. Okay, thank you.
Now we can fine. Okay, so and so I guess at the very okay, so the easy exercise says that this when I consider 1 over, I guess I want to square yes, square root of a k n over a and infinity is a orthonormal normal basis for and So in the Young's coefficient, and coefficient of f with respect to this basis, with respect to the basis, is the inner product between f and 1 over square root of a k n over a in L2 or in Filipino space, which is 1 over a times n over a. Okay. So by Fourier, by Hilbert space theory, Hilbert theory. We have that when I consider sum of f with this orthonormal system, k n over a converges, but this is 1 over a times sum over n of f n over a times this function here was okay, because I have this square root over there. Just a second, let me see something.
There shall be another square root.
Okay, because this is the orthonormal basis. So this is the, okay, this converges to f in L2 or in the Hilbert space. Well, that's a Hilbert space, right? It's it is expansion with respect to the spaces of the function f. Okay. But this is okay, this is 1 over square root of a, 1 over square root of a is 1 over a. But then this times that, it is, we said in the reducing formula, it is a times that times this, which is the sink of whatever. I'm sorry, this is a times sink of whatever it is. By a, I get it lost. It's by a t minus n over 30. So this is cancel out. It means that the series, okay, this is the Shannon series. It means that it converges in L2. Okay, so converges in L2 of R, and not just okay. So this is about sampling. What about interpolation? So about interpolation, I just tell you that everything we did so far suggests an interpolation formula. It means so far what we have so what do you see so far for the function f in the linear space we have vector we said that f of p can be reconstructed as the sum of fn over a times the distinct of that thing over there by a p times n, and we have the two norm of f is equal to 1 over a sum over n and over a. Well, so the function f can be reconstructed by its samples, and each sample satisfies this isometry relation. This suggests a formula for interpolation. So consider the sequence an, which is I think of an like this one, so that well normalized well of course a liberal sequence. I just normalize that is normal here and look for a function f in the linear space so that f of n over a is equal to an. So I want to solve this interpolation problem. How can I do it? Well, I copy this formula here. I say, well, seems that the best possible way is to define f of t as sum plus infinity of a n times c by a t minus n. This function f is in the linear space and it is in the linear space basically because this is an orthonormal basis for L2 of because this is an orthonormal person. This is an orthonormal for the linear. And so this is a sum of an orthonormal base converged in L2. Okay? So this is a series converged a priori in L2 or in very linear. So we solved our interpolation problem. Right. Okay. Angle, okay, this one. Angle. Well, by Shannon's formula, right? We have that f of t by Shannon theorem. We know that f of t is also equal to sum for n minus infinity plus infinity of n over a, can be the same thing. And because it's a linear space. Well, but then so that fn over a is equal to an for n. They are the coefficients of f with respect to the orthonormal basis. One equals an over a for maybe 1 over square root a. They are the same thing. And that's about the angle. Let me just make last observation, which is that there is a magic formula that you can give to your students if you teach analysis 1, mathematics. They come up with a so the magic formula is this one. It's close. It is that you think of by a x z is equal sum for n minus infinity plus infinity of think of phi n minus a times the think times the think of phi n how do you get this? I guess I fix right. So this is I apply and to the function maybe it was take exactly. There is something that not fun. Just a second, if I repeat something. Okay, for sure it works if A is equal to 1. K is not equal to 1. Okay. Because so if I let I want n over A here. Right, n over A, which gives that. Let's see. Yes. These are the samples. That's it. Yes. Well, exercise, check. Check if this is towards for A different than 1. Okay, and then this is all of these things will either Nikos or I will kind of we'll go quickly into the general theory of runtime of reproducing kernels, and many of these things they will become easier in the abstract theory. And some of these things they will become false, and some of these things will become very difficult, or even open problems. Okay.
There is a square. There must be a square. No.
Yeah, no, always have doubts. But this is exactly Shannon's one. So, yeah. Yeah, because there are decent square roots they cancel. When you do the orthonormal thing, they cancel out a lot of. Because they appear in the coefficient, they appear in the kernel function, but then you also have some A appearing somewhere. Well, if you find mistakes, let me know. Because I took the notes on the website.